Scientists pointed the most powerful space telescope ever built at one of the emptiest regions in the observable universe. They expected to confirm what every model predicted. Cosmic voids should be barren wastelands where almost nothing forms. Instead, the James Webb Space Telescope returned data that forced researchers to question how galaxies assemble inside the cosmic web. The galaxies Webb found within an underdense region were too structured, too chemically enriched, and too evolved for their desolate surroundings. Standard simulations never predicted this. The emptiest places in the cosmos are not behaving the way physics demands. What Webb observed inside a cosmic void challenges everything we thought we understood about how matter organizes itself across the universe. If you enjoy journeys into the deepest mysteries of the cosmos, consider hitting that like button and subscribing. It helps more than you know, and I genuinely appreciate every single one of you who joins this adventure. Now, get yourself comfortable. Let's begin. The universe is not what it looks like. Stand outside on a clear night and the sky appears crowded with stars. Every pinpoint of light suggests a cosmos packed with matter, dense with activity, filled from edge to edge with burning suns and spinning worlds. This impression is among the most convincing illusions in nature. It is created entirely by your position inside one of the busiest neighborhoods in the galaxy. The reality is the precise opposite. Most of the observable universe contains almost nothing. Between the glittering filaments of galaxies stretches a dominion of emptiness so vast that the human mind buckles under its scale. These regions are called cosmic voids. They are not small gaps between neighboring galaxy clusters. They are not modest pockets of slightly lower density. They are enormous spherical volumes hundreds of millions of light years across where matter is so scarce that gravity barely functions as a meaningful force. If you could somehow teleport to the center of a typical cosmic void and look outward in every direction with the most powerful telescope ever constructed, you would see almost nothing. No galaxies, no clusters, no glowing nebulae. Just darkness extending for tens of millions of light years in every direction before the faintest smudge of a distant galaxy wall appeared at the very limit of perception. This emptiness is not an accident. It is not a flaw in the distribution of matter. It is the fundamental architecture of reality itself. The universe built this way on purpose, if gravity and quantum mechanics can be said to have purpose. Understanding why requires a journey that begins at the very first fraction of a second after the Big Bang and extends across the full 13.8 billion year history of cosmic evolution. But the discovery that the universe organizes itself into filaments and voids arrived slowly, then all at once. For most of human history, astronomers assumed galaxies scattered randomly through space the way dust motes float through sunlight. Some regions might contain a few more galaxies, others a few less, but the overall distribution was thought to be roughly uniform. The technology to test this assumption simply did not exist until the late 1970s, when spectroscopic surveys allowed researchers to measure the distances to thousands of galaxies simultaneously for the first time. Before this breakthrough, astronomers could photograph the sky and see galaxies in 2 dimensions. They could note which galaxies appeared near each other on the celestial sphere, but apparent proximity on the sky is deeply deceptive. 2 galaxies that look adjacent in a photograph might actually be separated by billions of light years, one sitting in the cosmic foreground and the other impossibly far behind it. Only by measuring each galaxy's redshift, the stretching of its light caused by cosmic expansion, could scientists calculate true 3-dimensional positions and begin mapping the actual structure of the universe. The first systematic redshift surveys transformed cosmology overnight. In 1978, Stephen Gregory and Laird Thompson published observations revealing a striking and wholly unexpected pattern. Galaxies were not randomly distributed. They concentrated along walls and filaments surrounding enormous empty regions. The same year, independent work by other research teams confirmed the pattern from different parts of the sky. Everywhere astronomers looked with sufficient depth, the same architecture appeared. Matter clustered along thin surfaces and elongated threads. Emptiness filled the vast interiors between those threads. The Bootes void, identified in 1981 by Robert Kirshner and colleagues, provided one of the earliest and most dramatic examples of this cosmic emptiness. This region spans roughly 330 million light-years across while containing only around 60 confirmed galaxies. To grasp how empty that is, consider that a similarly sized volume in a typical filament region would contain thousands of galaxies, possibly tens of thousands. The Bootes void was so spectacularly barren that Kirshner reportedly questioned whether the data processing pipeline had malfunctioned. It had not. The void was real, the emptiness was genuine, and it was only the beginning. Throughout the 1980s and 90s, surveys grew progressively larger and more detailed. The Center for Astrophysics Redshift Survey mapped galaxies across significant portions of the sky, revealing what astronomers began calling the cosmic web. The metaphor was immediately intuitive. Galaxy distributions resembled a vast three-dimensional spider web, with thin strands of luminous matter stretching between dense intersections where galaxy clusters blazed with concentrated light. The spaces between those strands were the voids, enormous, dark, overwhelmingly empty. Then came the Sloan Digital Sky Survey, which began operations in the year 2000. This project would eventually create the most detailed three-dimensional maps of galaxy distributions ever assembled, spanning billions of light-years in every observed direction. The maps it produced were breathtaking and deeply unsettling in equal measure. Filaments twisted and branched through space like the circulatory system of some incomprehensibly vast organism. Galaxy clusters burned at the intersections where multiple filaments converged, forming the dense nodes of the web. And between all of this luminous structure, voids gaped open everywhere, dark spherical bubbles occupying the overwhelming majority of cosmic volume. The numbers that emerged from these surveys were staggering and have only been refined since. Voids occupy roughly 80% of the total volume of the observable universe. Some analyses push this figure closer to 90%, depending on how void boundaries are defined. The filaments and clusters and walls where galaxies concentrate make up the remaining 10 to 20% of the total volume, yet contain the vast majority of all mass. This creates a profoundly lopsided cosmos. Most of the space is empty. Most of the matter is crowded into a thin minority of the total volume. The universe resembles foam far more than it resembles fog, with thin bubble walls of matter surrounding enormous hollow interiors. The foam analogy deserves closer attention because it captures something essential about how the cosmos is organized, that simple descriptions of clusters and voids tend to miss. Imagine a bathtub filled with soap bubbles. The air inside each bubble represents a void. The thin soap film forming the bubble walls represents the filaments and sheets where galaxies concentrate. Where multiple bubbles press together, the films thicken slightly, forming the nodes where galaxy clusters accumulate. Now extend this image in 3 dimensions across a volume spanning billions of light-years, and you have a reasonable first approximation of the cosmic web. But unlike soap bubbles, which are roughly uniform in size, cosmic voids span an enormous range of scales. The smallest voids measure only 30 or 40 million light-years across, modest underdensities nested within the larger web, like tiny air pockets trapped within the film of a larger bubble. Medium-sized voids stretch across 100 to 300 million light-years, comprising the bulk of the void population catalogued by galaxy surveys. And at the extreme end, supervoids extend beyond 500 million light-years, rare colossal structures that occupy significant fractions of the observable volume in the directions they span. The Eridanus supervoid, one of the largest known, stretches roughly 1.8 billion light-years across and sits approximately 3 billion light-years from Earth. Its existence was inferred before it was directly confirmed. Detected through an anomalous cold spot, it imprints on the cosmic microwave background radiation as ancient photons lose energy traversing its expanding interior. This hierarchy of void sizes reflects the hierarchy of initial density fluctuations that seeded them. Small voids grew from small underdensities. Large voids grew from larger, rarer fluctuations that happened to produce substantial underdense regions across wider patches of the early universe. The distribution of void sizes constitutes a statistical record of the primordial density field, carrying information about the physics of cosmic inflation and the initial conditions from which all structure emerged. Understanding why the cosmos organizes itself this way requires traveling backward through time to the very first moments of existence. In the first fraction of a second after the Big Bang, during a period called cosmic inflation, the universe expanded exponentially. Space itself stretched at a rate so rapid that regions smaller than a single proton were inflated to volumes larger than the entire observable universe today, within a span of time almost too brief to express in conventional units. During this explosive expansion, quantum fluctuations, the inherent uncertainty that exists at the very foundation of physical reality, were stretched from subatomic dimensions to cosmic proportions. These inflated quantum fluctuations created slight variations in the density of matter and energy throughout the infant universe. In some regions, density ended up a tiny fraction higher than the cosmic average. In others, a tiny fraction lower. The differences were extraordinarily small, approximately 1 part in 100,000. If you could have measured the density at 2 different points in the early universe, they would have agreed to the 5th decimal place. The variations were almost immeasurably subtle, but almost immeasurable is not zero, and gravity has infinite patience. Gravity amplifies even the smallest advantages given sufficient time. Regions that started with density fractionally above the average exerted slightly stronger gravitational pull on their surroundings. That extra pull drew in matter from neighbouring regions, increasing the local density. The increased density strengthened the gravitational pull further, attracting still more material. A positive feedback loop locked into place. The denser a region became, the more aggressively it harvested matter from its environment, making itself denser still. Meanwhile, regions that started with density fractionally below the average experienced the mirror image of this process. Matter drained away from them toward the growing overdensities. As material departed, these underdense regions became progressively emptier. Their weakening gravity could not compete with the pull from surrounding concentrations of matter. They were losing a competition they could never win, outbid at every turn by regions that started with even the slightest advantage. Over hundreds of millions of years, this gravitational sorting transformed barely perceptible initial ripples into the dramatic, large-scale structure visible today. The overdense regions collapsed into the first dark matter halos, then the first stars, then the first galaxies, then galaxy groups and clusters. These structures aligned along filaments and walls, tracing out the skeleton of the cosmic web. The underdense regions expanded into voids, growing larger and emptier as matter continued draining toward the filaments. The process is called gravitational instability, and it turned quantum whispers from the universe's first heartbeat into the grandest architecture in existence. The cosmic web that spans billions of light years and contains trillions of galaxies traces its origin to random fluctuations smaller than an atom that occurred in a time interval, shorter than any clock could measure. Everything that exists, every galaxy, every star, every planet, every void, descends from those primordial quantum ripples amplified by relentless gravity across cosmic time. The cosmic microwave background radiation provides direct observational evidence of these density variations when the universe was only 380,000 years old. At that epoch, the cosmos cooled enough for the first stable atoms to form, and the universe became transparent to light for the first time. The radiation released at that moment has been travelling through space ever since, stretched by cosmic expansion into microwave wavelengths. It fills the entire sky with a faint glow at a temperature of approximately 2.7 Kelvin, just above absolute zero. This glow is not perfectly uniform. Satellites, including the Cosmic Background Explorer, the Wilkinson Microwave Anisotropy Probe, and the Planck spacecraft, mapped temperature variations across the entire sky with extraordinary precision. The fluctuations are tiny, typically only a few hundred thousandths of a degree from one direction to another, but they encode an immense amount of information. Warmer spots corresponded to regions that were slightly denser than average when the light was released. Cooler spots corresponded to regions that were slightly less dense. These temperature maps show the seeds of everything that would follow, the places where filaments and clusters would eventually grow, the places where voids would eventually open. Scientists can take these maps and feed them into computer simulations that model how gravity shapes matter over the subsequent 13 billion years. The simulations begin with initial conditions matching the observed cosmic microwave background pattern, then evolve the matter distribution forward in time using the laws of gravitational physics, gas dynamics, and cosmic expansion. The results are remarkable. The simulations reliably produce a cosmic web of filaments, clusters, walls, and voids that closely resembles the actual universe mapped by galaxy surveys. This agreement between prediction and observation ranks among the great triumphs of modern cosmology. It demonstrates that we understand, in broad strokes, how the universe assembled itself from nearly featureless initial conditions into the structured cosmos we inhabit. The Lambda Cold Dark Matter model, the standard framework of cosmology, passes this test with impressive fidelity. But understanding how voids form at a general level is very different from understanding what happens inside them in detail. The interior of a cosmic void is a genuinely strange place for physics. Matter density sits at roughly 10 to 20% of the cosmic average, depending on the void's depth and how far from its center you measure. Dark matter is present but thinly spread across an immense volume, too dilute to create the deep gravitational wells found in filaments and clusters. Normal matter, the atoms and molecules from which stars and planets are built, is scarcer still. A few lonely galaxies drift through the vast interior, separated by distances that dwarf the gaps between galaxies in typical environments. The contrast with life inside a filament could not be sharper. A galaxy residing in a dense filament or cluster environment exists in a crowded, violent, dynamic neighborhood. It experiences frequent gravitational encounters with passing neighbors. It may undergo full-scale mergers with other galaxies. Events that scramble its internal structure, trigger explosive bursts of star formation, and funnel gas toward its central supermassive black hole. Hot intergalactic gas surrounding the galaxy in a cluster environment exerts ram pressure that can strip cold gas from its disk, choking off the fuel supply for future star formation. The galaxy evolves rapidly, driven by forces imposed from outside. A galaxy inside a void experiences none of this. Its nearest neighbor might sit tens of millions of light-years away, too distant for any gravitational interaction to occur on relevant timescales. No mergers threaten its structure. No intergalactic medium exerts pressure on its gas. No tidal forces distort its shape. The galaxy evolves in near-perfect isolation, shaped almost entirely by its own internal processes rather than external influences. It forms stars from whatever gas it can accumulate, at whatever rate its own gravity and cooling physics permit, without the dramatic accelerants or suppressants that dense environments provide. This isolation produces observable differences. Surveys of galaxies in nearby voids, within a few 100 million light-years of Earth, have confirmed that void galaxies differ systematically from their counterparts in denser environments. They tend to be smaller, containing fewer stars and less total mass. They appear bluer in colour, indicating younger stellar populations and ongoing star formation, rather than the red, quiescent populations dominated by old stars that characterise massive galaxies and clusters. They retain large reservoirs of neutral hydrogen gas that has not yet condensed into stars, fuel that would have been consumed or stripped long ago in a denser neighbourhood. Their chemical compositions reflect their slower pace of evolution. Metallicities, the abundances of elements heavier than helium produced inside stars and distributed through supernovae, are systematically lower in void galaxies than in galaxies of comparable mass in filaments. Fewer generations of stars have completed their life cycles. Less nuclear processing has occurred. The galaxy's chemical clock runs slower in the void because there is less raw material to work with, and fewer environmental triggers to accelerate the process. Morphologically, void galaxies are overwhelmingly disk-dominated spirals and irregulars. The elliptical galaxies common in cluster cores, products of violent major mergers, are nearly absent from void populations because the mergers required to create them almost never happen in such sparse environments. Void spirals often display remarkably undisturbed disk profiles with symmetric spiral arms and regular rotation patterns, reflecting billions of years of evolution unperturbed by external gravitational forces. These nearby void galaxy observations aligned well with theoretical predictions. The standard framework predicted that void environments should produce smaller, bluer, more gas-rich, less chemically enriched, more disk-dominated galaxy populations. Observations confirmed exactly that. The agreement reinforced confidence that void galaxy physics was well understood. In this sparse landscape, dark energy rules without meaningful opposition. Dark energy, the mysterious component accounting for approximately 68% of the universe's total energy content, drives cosmic expansion and pushes space apart. In dense environments like galaxy clusters, gravity fights back against this expansion. The concentrated mass of thousands of galaxies and their dark matter halos creates gravitational pull strong enough to overcome dark energy locally, holding clusters together despite the stretching of space around them. Inside voids, this contest is no contest at all. There is simply not enough mass to resist dark energy's outward pressure. The result is a self-reinforcing cycle that makes voids grow over time. As a void expands under dark energy's influence, it becomes emptier. The matter within it spreads across a larger volume, reducing the local density further. Lower density means weaker gravitational resistance to continued expansion. Weaker resistance means faster growth. The void swells, becoming even emptier, which reduces gravitational resistance further still. This feedback loop has been operating for billions of years, and it continues today. Voids are not static relics of the early universe. They are dynamic, evolving structures that expand steadily, pushing their boundaries outward while the surrounding filaments act as confining walls. This expansion has observable consequences. Galaxies near the edges of voids experience outward peculiar velocities, meaning they move faster away from the void center than cosmic expansion alone would predict. The gravitational pull from the denser material in surrounding filaments and walls tugs these edge galaxies outward, away from the underdensity and toward the concentrations of matter beyond. Scientists can detect this outflow by carefully comparing galaxy redshifts with independent distance measurements. The velocity patterns around known voids match the predictions of gravitational physics precisely. Light traveling through voids also behaves in measurably different ways. Photons from the cosmic microwave background that pass through an expanding void experience a subtle energy loss through a process called the integrated Sachs-Wolf effect. When a photon enters a void, it gains a tiny amount of energy falling into the gravitational potential, well, shallow as it is. When it climbs back out on the other side, it loses energy. If the void were static, these two effects would cancel exactly, and the photon would emerge unchanged. But the void expands while the photon traverses it. The potential well becomes shallower during the crossing. The photon loses slightly more energy climbing out than it gained falling in. It emerges with a small net energy deficit, which appears as a tiny temperature decrement in the cosmic microwave background. These cold spots correlate with the positions of known large voids identified through galaxy surveys. The correlation has been confirmed statistically across multiple independent analyses. The physics is clean, well understood, and experimentally verified. Voids leave their fingerprints on the oldest light in the universe. All of this painted a picture that seemed comprehensive and self-consistent. Cosmic voids are enormous, mostly empty, dominated by dark energy steadily expanding, and home to very few galaxies. The few galaxies that do manage to form inside voids should be small, dim, rich in unprocessed hydrogen gas, and slowly evolving compared to their counterparts in denser environments. They should lack the violent gravitational interactions and frequent mergers that drive rapid galaxy evolution in clusters and filaments. They should represent the cosmic backwaters, quiet places where very little happens on galactic timescales. For decades, this expectation held firm. The observations of nearby void galaxies confirmed the broad predictions. Scientists grew confident in the completeness of their understanding. Voids were regarded as the simplest environments in the cosmos. Their low density made them predictable. Their isolation made them clean. Whatever happened in voids should be easy to model because so little happened there at all. The confidence in void predictability was not arrogance. It was the natural and reasonable result of a model that worked remarkably well across an enormous range of observations. Lambda Cold Dark Matter successfully explained the temperature fluctuations in the cosmic microwave background. It accounted for the observed abundances of light elements like hydrogen and helium produced in the first minutes after the Big Bang. It reproduced the large-scale distribution of galaxies across the cosmic web. It predicted the accelerating expansion of the universe driven by dark energy. When a theoretical framework succeeds this comprehensively, across so many independent lines of evidence, scientists rightly trust its predictions for regimes they have not yet observed in detail. Voids at intermediate and high redshifts, meaning voids as they existed billions of years ago when the universe was significantly younger, represented exactly such an unobserved regime. Telescopes before Webb lacked the sensitivity and angular resolution to characterize the properties of individual faint galaxies within distant underdense regions. The predictions from simulations stood largely untested at these earlier cosmic epochs. Scientists had no reason to doubt them, but they also had no direct confirmation. The standard expectation for these distant void galaxies was unambiguous. Structure formation proceeds from the densest environments outward. The first massive galaxies should appear at the densest nodes of the cosmic web, where matter concentrated earliest and gravity worked fastest. Voids, perpetually starved of raw material and gravitational depth, should lag behind at every evolutionary stage. Void galaxies observed at higher redshifts, when the universe was younger and less evolved overall, should appear even less developed than their nearby counterparts, less massive, less chemically enriched, less structurally complex. This expectation became one of the implicit assumptions built into hundreds of published papers and dozens of simulation suites used by research groups around the world. It seemed so straightforwardly logical that few researchers bothered to state it explicitly or treat it as something requiring observational verification. Emptier regions produce less developed galaxies. Denser regions produce more developed galaxies. The relationship should scale smoothly and predictably with environment. But implicit assumptions are precisely the assumptions most vulnerable to surprise. They persist not because they have been rigorously tested, but because nobody has yet gathered the data needed to challenge them. They survive through absence of contradiction rather than presence of confirmation, and they can endure for decades until a single observation forces them into the open where they must defend themselves against evidence. The observational gap was real and well recognized. No telescope before Webb possessed the combination of infrared sensitivity, angular resolution, and spectroscopic power needed to characterize individual faint galaxies within distant underdense regions. Scientists had detailed observations of void galaxies nearby and robust theoretical predictions for void galaxies far away, but almost nothing connecting the two. The predictions occupied uncontested space, accepted by default because no observation existed to challenge them. The James Webb Space Telescope was built to fill exactly these kinds of gaps. It was the first space observatory designed from the ground up to combine a very large infrared optimized mirror with the spectroscopic power needed to characterize faint, distant galaxies at the individual level. Everything about its design, from its orbital position far from Earth to its suite of infrared instruments, was engineered to reach the objects and environments that previous telescopes could not. When Webb began its science operations in the summer of 2022, it carried the capacity to test assumptions that had remained untested for decades. The void predictions were among them, not because anyone expected a surprise, but because comprehensive science demands that predictions be checked against reality rather than accepted on theoretical faith alone. What nobody anticipated was how quickly that faith would be tested. When Webb turned its instruments toward galaxies within a known underdense region at intermediate redshift, it had the power to measure individual void galaxy properties with a precision no telescope had ever achieved for objects in such sparse environments. The data it returned would not shatter the standard model. It would not overthrow decades of cosmological success, but it would reveal something that simulations never predicted, and that theorists are still working to explain. The emptiest places in the cosmos were keeping a secret, and the most powerful observatory in human history had just uncovered it. Cosmic voids might seem like the least rewarding targets in all of observational astronomy. They contain almost nothing visible. They produce almost no detectable light. They lack the violent collisions, spectacular starbursts, and gravitational theatrics that make dense environments visually stunning and scientifically productive. A reasonable person might wonder why any research team would spend precious telescope time staring at regions defined primarily by what they do not contain. The answer reveals one of the most important and least appreciated insights in modern cosmology. Voids are not scientifically barren. They are uniquely valuable. They represent the only environments in the observable universe where one of nature's most mysterious forces operates essentially unopposed, and measuring how that force behaves in these pristine conditions could unlock answers to questions that have frustrated physicists for more than a quarter century. That force is dark energy. Part 1 established that dark energy dominates the interior of cosmic voids because matter density is too low for gravity to mount effective resistance. But stating that dark energy dominates is very different from explaining why that dominance makes voids scientifically irreplaceable. The distinction matters enormously, and it begins with a problem that has haunted cosmology since 1998. When two independent research teams discovered that the expansion of the universe was accelerating rather than decelerating, the finding demanded an explanation. Something was pushing space apart faster and faster over time. That something was given the placeholder name dark energy, a label that conceals profound ignorance behind a veneer of terminology. We know dark energy exists because we observe its effects. We know it constitutes approximately 68% of the universe's total energy budget. We know it behaves in a way that is fundamentally unlike any form of matter or radiation ever studied in a laboratory. But we do not know what it is. The simplest theoretical candidate is the cosmological constant, a fixed energy density inherent to the fabric of space-time itself. In this picture, every cubic meter of space contains the same tiny amount of dark energy, regardless of what else that volume contains. The cosmological constant does not dilute as space expands, because new space comes preloaded with the same energy density. It does not clump or cluster. It does not interact with matter, except through its gravitational effect on cosmic expansion. If the cosmological constant is the correct description, dark energy has been the same strength throughout cosmic history and will remain the same strength forever. The universe will continue accelerating, galaxies will continue separating, and the eventual fate of the cosmos will be a cold, dark, infinitely expanding void. But this is not the only possibility. Alternative models propose that dark energy is dynamic, meaning its strength changes over time, or varies from place to place. Some theories describe dark energy as a quantum field called quintessence that evolves as the universe expands. In these models, dark energy was weaker in the past and has been growing stronger, or it was stronger in the past and has been weakening, or it oscillates between stronger and weaker phases over cosmic timescales. Each scenario produces a different future for the universe and a different history of cosmic structure formation. Distinguishing between a cosmological constant and dynamic dark energy is one of the highest priority goals in modern physics. The answer determines whether the universe's fate is eternal expansion, eventual collapse, or something more exotic that current theory has not fully anticipated. Hundreds of researchers across dozens of institutions are working on this problem using multiple complementary approaches, and cosmic voids offer what may be the cleanest avenue to a solution. The logic is straightforward. To measure dark energy's properties, scientists need to observe how cosmic expansion accelerates under different conditions and at different epochs. In dense environments, the measurement is contaminated by gravity. Galaxy clusters, filaments, and walls contain enormous concentrations of mass that pull on surrounding matter, creating local gravitational effects that must be carefully modeled and subtracted before the dark energy signal can be extracted. This subtraction introduces uncertainty. Every assumption built into the gravitational model carries potential error that propagates into the dark energy measurement. Inside voids, the gravitational contamination largely disappears. The matter density is so low that local gravitational effects become negligible compared to dark energy's influence on expansion. Galaxies within voids move almost entirely in response to cosmic expansion and dark energy. Their velocities trace the dark energy signal with far less gravitational noise than equivalent measurements in dense environments. The laboratory is cleaner, the signal is purer, the conclusions are more robust. This advantage manifests in several specific measurement techniques that exploit void properties. Void expansion rates provide a direct probe of dark energy strength. Scientists can measure how fast a void is growing by tracking the motions of galaxies at its boundaries over cosmic time. If dark energy is a cosmological constant, voids at a given depth should expand at a rate calculable from first principles using the known energy density and the equations of general relativity. If the observed expansion rate differs from this prediction, dark energy must be dynamic, either stronger or weaker than the constant value at the epoch being measured. Comparing void expansion rates at different redshifts, which correspond to different cosmic times, creates a timeline of dark energy's behavior across billions of years. Void geometry offers a complementary measurement. If dark energy is truly uniform and isotropic, voids should expand at the same rate in every direction, maintaining roughly spherical shapes as they grow. Deviations from spherical symmetry would indicate that dark energy has spatial structure, varying in strength from one direction to another, or that unknown forces are acting on cosmological scales in ways current theory does not anticipate. Measuring the three-dimensional shapes of large void samples at various redshifts constrains the isotropy of dark energy with a sensitivity that dense environment measurements cannot match. The stacking technique amplifies these measurements further. Individual voids are noisy. Each one has a unique shape, depth, and galaxy population influenced by its specific formation history and local environment. But when scientists stack hundreds or thousands of voids, aligning them by their centers and averaging their properties, the individual noise cancels while the systematic dark energy signal reinforces. Stacked void profiles reveal the average expansion rate, density gradient, and boundary sharpness, with statistical precision far exceeding what any single void could provide. Large galaxy surveys like the Sloan Digital Sky Survey and the Dark Energy Spectroscopic Instrument have enabled stacking analyses involving thousands of voids, producing some of the tightest constraints on dark energy behavior currently available. Baryon acoustic oscillations provide yet another measurement avenue, and voids play a specific role in how this tool functions. Baryon acoustic oscillations are frozen sound waves from the infant universe. In the first 380,000 years after the Big Bang, matter and radiation were coupled together in a hot, dense plasma. Sound waves rippled through this plasma at roughly half the speed of light, creating oscillating patterns of compression and rarefaction. When the universe cooled enough for atoms to form and radiation decoupled from matter, these sound waves froze in place. The distance each wave had traveled before freezing, approximately 490 million light-years in today's expanded coordinates, left an imprint on how matter distributes itself throughout the cosmos. This characteristic distance appears as a subtle statistical excess in the probability of finding two galaxies separated by that specific scale. It functions as a cosmic ruler because the physics that created it is thoroughly understood. Scientists can measure the apparent size of this ruler at different redshifts and compare it to its known physical length. The comparison reveals how much space has expanded between the ruler's epoch and the observation epoch. By tracking how this expansion changes over cosmic time, researchers can map the acceleration history driven by dark energy. Here is where voids become specifically important. The baryon acoustic oscillation signal appears slightly differently in void environments compared to average density regions. Inside voids, the expansion of space has been faster than average because dark energy faces less gravitational opposition. This faster expansion stretches the acoustic ruler, making it appear slightly larger inside voids than in filaments or clusters at the same redshift. Measuring this environmental dependence of the baryon acoustic oscillation scale provides a differential test of dark energy's behavior, comparing its effects in low-density versus high-density regions within the same cosmic volume. If dark energy is a simple cosmological constant, the ratio between the void-measured and filament-measured baryon acoustic oscillation scales should follow a precise mathematical relationship determined entirely by the density contrast between the two environments. If the observed ratio deviates from this prediction, dark energy must behave differently in different density environments, which would rule out the cosmological constant and point toward dynamic models. Current measurements are approaching the precision needed to distinguish between these scenarios. The dark energy spectroscopic instrument is mapping tens of millions of galaxy positions and redshifts with spectroscopic accuracy across a substantial fraction of the observable sky. This unprecedented dataset will identify thousands of voids across a wide range of redshifts and measure baryon acoustic oscillation scales within each of them. Within the next several years, the resulting constraints on dark energy properties will either confirm the cosmological constant to new levels of precision or reveal deviations that demand new physics. The Euclid Space Telescope, launched in July of 2023, adds another dimension. Euclid combines spectroscopic galaxy surveys with weak gravitational lensing measurements, mapping the subtle distortions that large-scale mass concentrations impose on the shapes of background galaxies. Voids produce a specific lensing signature, a slight defocusing effect that causes background galaxies to appear marginally more circular than they would otherwise. This void lensing signal measures the total mass content of void regions, including dark matter, providing constraints on cosmic matter distribution that complement the expansion rate measurements from baryon acoustic oscillations. Together, these techniques transform voids from apparently featureless emptiness into precision instruments for measuring the most mysterious component of the universe. Every void in the cosmos is a dark energy laboratory. The deeper the void, the cleaner the measurement. The more voids surveyed, the tighter the constraints. The scientific value of emptiness turns out to be immense. But dark energy studies represent only half of why voids matter scientifically. The other half involves what voids reveal about structure formation, the process by which gravity converts the nearly uniform matter distribution of the early universe into the galaxies, clusters, and cosmic web we observe today. Lambda Cold Dark Matter makes specific, quantitative, testable predictions about the galaxy populations that should exist inside cosmic voids. These predictions emerge naturally from the model's treatment of dark matter halo formation, gas accretion, star formation, and feedback processes. They are not vague qualitative expectations. They are precise numerical forecasts for observable galaxy properties as functions of environment, mass, and cosmic epoch. The predictions begin with dark matter halos. In Lambda CDM, galaxies do not form in isolation. They form inside gravitationally bound concentrations of dark matter called halos. The abundance of these halos at any given mass, called the halo mass function, depends sensitively on the local matter density. In overdense regions, the halo mass function extends to very high masses, producing the enormous halos that host massive galaxy clusters. In average density regions, the mass function is shifted downward, producing fewer massive halos but abundant intermediate mass systems. In voids, the mass function shifts further down still. The underdense environment suppresses the formation of massive halos because there is simply insufficient matter available for gravity to assemble large concentrations. This suppression creates a ceiling on the masses of galaxies that can form inside voids. The most massive void halos in standard simulations typically reach only a fraction of the mass of the most massive halos in filaments at the same cosmic epoch. This mass ceiling cascades through every aspect of galaxy formation because halo mass governs how much gas a galaxy can attract, how deeply that gas can fall into the gravitational well, how efficiently it can cool and condense into star-forming clouds, and how effectively supernova feedback can expel processed material. Gas accretion in void environments differs fundamentally from accretion in denser regions. In filaments and clusters, galaxies grow partly through what cosmologists call hot mode accretion. Gas falling into massive halos gets shock heated to millions of degrees, forming a diffuse atmosphere that cools gradually and settles onto the central galaxy over extended timescales. This process is efficient for massive halos but operates differently in the shallow potential wells characteristic of void environments. Void halos are generally not massive enough to sustain stable, shock-heated atmospheres. Instead, their gas arrives through cold mode accretion, streaming along narrow filaments directly into the galaxy without significant shock heating. Cold mode accretion is fundamentally different in character. It delivers gas at lower temperatures and higher densities, potentially fueling star formation more directly than hot mode accretion. But the total amount of available gas is constrained by the sparse environment. A void galaxy's cold mode accretion draws from a much smaller reservoir than equivalent accretion in a filament. The result, according to simulations, is steady but modest star formation sustained over long periods, rather than the intense episodes triggered by mergers and hot gas cooling in dense environments. Star formation histories in void galaxies should consequently follow a distinctive pattern. Rather than experiencing the early intense burst followed by gradual decline characteristic of massive galaxies in dense environments, void galaxies should build their stellar mass slowly and steadily. Their star formation rates should remain low but persistent, converting gas into stars at a measured pace determined by the balance between cold accretion supply and supernova-driven outflow. This gradual formation history produces specific observable signatures. The stellar populations in void galaxies should be weighted toward younger ages on average, because the extended star formation means a significant fraction of the total stellar mass was assembled relatively recently. The luminosity-weighted ages, which reflect the average formation epoch of the brightest stars, should be younger than equivalent measurements for galaxies of similar mass in filaments. Spectroscopic indicators sensitive to stellar age, such as the strength of the 4,000 angstrom break or the equivalent widths of hydrogen absorption lines, should differ systematically between void and non-void populations. Chemical enrichment predictions follow directly from the star formation history expectations. Heavy elements, everything astronomers call metals, are produced inside stars through nuclear fusion and return to the interstellar medium when those stars die. The metallicity of a galaxy's gas and stars is fundamentally a cumulative record of how many stellar generations have lived and died within it, modulated by how much enriched gas has been expelled by supernova-driven winds and how much pristine gas has been accreted from the external environment. In void galaxies, the slower star formation pace means fewer stellar generations have completed their life cycles by any given cosmic epoch. Fewer completed generations means less cumulative heavy element production. Lower production, combined with the shallow gravitational wells that make expelling enriched gas through supernova feedback relatively easy, should produce metallicities systematically below the values found in galaxies of comparable stellar mass in denser environments. This prediction is quantitatively specific. The mass-metallicity relation, one of the most fundamental empirical correlations in galaxy physics, describes how the average gas phase oxygen abundance of a galaxy scales with its stellar mass. More massive galaxies generally have higher metallicities because their deeper gravitational wells retain more processed gas. Lambda CDM simulations predict that this relation should shift downward in void environments, meaning that at any given stellar mass, void galaxies should have lower metallicities than their counterparts in filaments by a measurable and predictable amount. The magnitude of this offset depends on the void depth, the galaxy mass, and the cosmic epoch, but the direction is consistent. Voids should produce chemically immature galaxies. Morphological predictions add another layer of specificity. Galaxy structure is shaped by both internal processes and external interactions. In dense environments, frequent gravitational encounters between galaxies drive morphological transformation. Minor mergers build bulge components through dynamical heating of disk stars. Major mergers destroy disk structures entirely, scrambling organized orbital motion into the random trajectories characteristic of elliptical galaxies. Harassment from repeated high-speed encounters in cluster environments strips outer disk material and disrupts spiral arm patterns. None of these environmental processes operates efficiently inside voids. Galaxies are too few and too widely separated for frequent encounters. Major mergers are extraordinarily rare. Minor mergers occur but at rates far below those in filaments. Cluster-style harassment is absent entirely because voids do not contain clusters. The morphological consequence is straightforward. Void galaxies should be overwhelmingly disk-dominated. Spiral galaxies and irregular systems should vastly outnumber elliptical galaxies. Among the spirals, morphologies should be relatively undisturbed, with symmetric disk profiles, regular rotation curves, and well-organized spiral arm patterns reflecting billions of years of unperturbed evolution. Bulge-to-disk ratios should be low because the mechanisms that build bulges, mergers, and dynamical heating operate weakly in the void environment. Some void galaxies might show evidence of internal secular evolution, the slow redistribution of angular momentum within a disk that can build pseudo-bulge structures over billions of years without any external trigger. Bars, oval distortions in the inner disk, drive gas inward and gradually construct central mass concentrations. This process operates independently of environment and should be present in void galaxies as readily as anywhere else. But the resulting pseudo-bulges are structurally distinct from the classical bulges built through mergers, and careful morphological analysis can distinguish between them. The combination of all these predictions created a detailed, multi-dimensional expectation that aligned well with observations of nearby void galaxies, as described earlier. The agreement between theory and observation in the local universe was encouraging, though not without minor tensions. Some nearby void galaxies showed slightly higher star formation rates than expected, concentrated in starburst episodes that seemed inconsistent with the gradual formation picture. A handful displayed unexpectedly high metallicities that fell above the predicted mass-metallicity relation for their environment. These anomalies were noted in the literature but generally attributed to normal statistical variance within a population that broadly matched expectations. The critical limitation was distance. All the successful comparisons involved relatively nearby voids where galaxies could be studied in detail with existing instrumentation. At intermediate and high redshifts, where the universe was substantially younger and structure formation less advanced, detailed void galaxy characterization remained beyond observational reach. This was not a minor gap. The intermediate redshift regime is where differences between cosmological models often manifest most clearly. If star formation in void environments proceeds differently than simulations predict, the discrepancy between observation and theory might be small at late cosmic times. When galaxies have had billions of years to evolve and various effects can average out, but large at earlier times when differences in formation efficiency have had less time to be diluted. The blind spot persisted not because scientists were unaware of it, but because the technology required to eliminate it simply did not exist. Filling the gap demanded a very specific combination of capabilities that no single observatory possessed. The telescope needed to operate in the infrared, because the diagnostic spectral features of galaxies at intermediate redshifts shift out of the optical window and into wavelengths ranging from 1 to 5 microns. It needed to sit above Earth's atmosphere because water vapor and thermal emission from the atmosphere itself create overwhelming background noise at precisely those infrared wavelengths. It needed a primary mirror large enough to collect sufficient photons from intrinsically faint void galaxies at distances of several billion light-years. And it needed a spectrograph capable of dispersing that faint light into wavelength components detailed enough to measure emission line ratios, absorption features, and continuum shapes from which physical properties could be derived. Every existing facility fell short on at least one of these requirements. The Keck Observatory in Hawaii and the Very Large Telescope in Chile possessed mirrors large enough for deep spectroscopy of faint objects. Their instruments included infrared spectrographs of considerable power, but they sat beneath Earth's atmosphere. The infrared sky from the ground is bright, noisy, and riddled with absorption bands from atmospheric water vapor and carbon dioxide. Detecting the faint emission lines of distant void galaxies against this atmospheric foreground required exposure times so long that the observations became impractical for any meaningful sample size. A single void galaxy might require an entire night of integration to produce a spectrum of marginal quality. Characterizing a statistically useful population of dozens of void galaxies at intermediate redshift would consume months of competitive telescope time that allocation committees were understandably reluctant to grant for targets with no guarantee of interesting results. The Hubble Space Telescope solved the atmosphere problem by operating in orbit. Its imaging capabilities in the optical and near-infrared were superb. Hubble's deep field campaigns revealed galaxies at extraordinary distances with exquisite resolution. But Hubble's mirror measured only 2.4 meters in diameter, limiting its light-collecting power for spectroscopy of the faintest objects. More critically, Hubble's spectroscopic instruments operated primarily at optical wavelengths. Its near-infrared GRISM provided low-resolution spectroscopy out to approximately 1.7 microns, but the spectral resolution was insufficient to resolve the individual emission lines needed for metallicity diagnostics. Hubble could photograph distant void galaxies, but it could not dissect their light with the precision required to measure their chemical compositions and star formation histories. The Spitzer Space Telescope operated entirely in the infrared from a heliocentric orbit that provided the cold thermal environment necessary for sensitive mid-infrared observations. Spitzer's contributions to galaxy evolution studies were enormous, but its primary mirror measured only 85 centimeters across. The resulting angular resolution, roughly 2 arc-seconds in the near-infrared, could not resolve the internal structures of galaxies at intermediate redshifts. A void galaxy at several billion light-years distance subtended only a fraction of an arc-second on the sky. In Spitzer's images, it appeared as an unresolved point of light, indistinguishable from a star. Morphological analysis was impossible. Even photometric measurements were compromised by confusion with overlapping sources in crowded fields. Each telescope offered part of what was needed. None offered the complete package. The infrared sensitivity existed on the ground, but was crippled by the atmosphere. The atmospheric freedom existed in space, but came with mirrors too small for faint spectroscopy or resolution too coarse for structural analysis. The gap persisted because it sat at the intersection of multiple technological limitations that could only be solved simultaneously by a facility designed from the ground up to address all of them at once. That facility was the James Webb Space Telescope, and it spent more than 2 decades in development precisely because the engineering challenges of building a 6.5-meter cryogenic infrared telescope that could be folded into a rocket fairing and deployed at a gravitational balance point 1.5 million kilometers from Earth were among the most demanding in the history of scientific instrumentation. During those 2 decades of development, simulations of void galaxy populations grew increasingly sophisticated. Hydrodynamic codes incorporated more detailed treatments of gas physics, star formation, and feedback. Computational volumes grew larger, capturing more voids with better statistical sampling. Resolution improved, resolving smaller halos and finer gas dynamics. Each generation of simulations produced updated predictions for what void galaxies should look like at intermediate and high redshifts. And each generation of predictions went untested because the telescope that could test them was still being assembled in clean rooms and tested in vacuum chambers. The predictions accumulated, papers were published, cited, and built upon. The theoretical picture solidified into something resembling consensus. Void galaxies at intermediate redshift should be small, blue, gas-rich, metal-poor, and disk-dominated. The expectation became so well established that it functioned less as a hypothesis to be tested and more as a boundary condition to be assumed in adjacent research programs. Models of galaxy evolution across all environments took the void predictions as given. Studies of dark energy using void properties assumed the void galaxy populations were correctly modeled. The untested predictions became load-bearing elements in a larger theoretical structure. This is a pattern that appears repeatedly in the history of science. When predictions cannot be tested, they do not remain cautious hypotheses hedged with uncertainty. They harden. They become reference values. They get embedded in other calculations. And when the test finally arrives, the stakes are higher than anyone initially intended because an entire scaffolding of subsequent work depends on the prediction being correct. Simulations of void galaxy populations at intermediate redshift made predictions that extended the local framework backward in time. At these earlier epochs, when the universe was roughly half its current age, void galaxies should be even less evolved than their nearby counterparts. Less time for star formation means lower stellar masses. Fewer completed stellar generations means lower metallicities. Less opportunity for secular evolution means simpler morphologies. Every property should shift further from the mature, evolved end of the galaxy population spectrum. These predictions rested on the combined machinery of Lambda CDM structure formation, hydrodynamic gas physics, and subgrid models for star formation and feedback. They were computed using the most sophisticated simulation codes available, run on some of the most powerful supercomputers in the world. They represented the consensus output of a theoretical framework that had been refined over 3 decades of increasingly precise comparison with observational data. The predictions were specific, they were quantitative, and they were testable, given a telescope with sufficient infrared sensitivity, angular resolution, and spectroscopic capability to characterize faint galaxies within distant, underdense regions at the level of individual objects rather than statistical averages. For years, that telescope did not exist. The predictions occupied a comfortable theoretical space where they could neither be confirmed nor contradicted. They were accepted not because evidence supported them at those redshifts, but because the framework that generated them had proven reliable in every other context where testing was possible. Then the James Webb Space Telescope began its science operations. And for the first time in the history of cosmology, researchers could examine what void galaxies actually looked like when the universe was billions of years younger. The expectation was clear and unambiguous. Webb should find undersized, chemically immature, structurally simple galaxies evolving slowly in their isolated environments. The void should look like a cosmic nursery that started late and progressed slowly, filled with galactic adolescents that had not yet grown into the modestly developed systems observed in nearby voids at the present epoch. If Lambda CDM was correct, the void at intermediate redshift should be the least interesting place Webb could point. A confirmation of predictions, a validation of models, a reassuring checkmark in the ledger of standard cosmology. The telescope was pointed, the data were collected. The photons that had travelled billions of years from galaxies drifting through one of the emptiest regions in the cosmos finally landed on Webb's detectors. And when researchers reduced the data, calibrated the spectra, fitted the models, and compared the results against the predictions they had trusted for decades, the numbers did not agree. Not catastrophically, not in a way that broke physics or violated conservation laws or suggested the models were entirely wrong, but systematically, consistently, and across multiple independent galaxy properties simultaneously, The observations exceeded what the models predicted. The void galaxies were more evolved than they had any right to be, and explaining why would require scientists to re-examine assumptions they had not questioned in years. The James Webb Space Telescope arrived at its operational orbit around the second Lagrange point in January of 2022, after a journey of roughly 1 million miles from Earth. Over the following 2 weeks, engineers methodically unfolded its sunshield and deployed its 18 hexagonal mirror segments into a single 6.5-meter collecting surface. The subsequent 5 months were spent aligning those segments to function as a unified mirror, calibrating instruments and cooling the observatory to the cryogenic temperatures required for infrared observation. By July of that year, the telescope began returning science data. Within weeks, it was producing results that unsettled multiple branches of astrophysics simultaneously. The telescope's capabilities represented a generational leap over every instrument that preceded it. Its primary mirror collected approximately 6 times more light than the Hubble Space Telescope. Its infrared instruments operated across wavelengths ranging from 0.6 of a micron to 28 microns, spanning the near-infrared and mid-infrared bands where the most diagnostically valuable features of distant galaxies appear after being stretched by cosmic expansion. Its near-infrared spectrograph could obtain simultaneous spectra of more than 200 objects across its field of view, a multiplexing advantage that made surveys of faint galaxy populations feasible within realistic observing timelines. For the study of distant void galaxies specifically, 2 capabilities mattered above all others. The first was sensitivity. Webb could detect galaxies at intermediate redshifts that were 10 to 100 times fainter than the detection limits of previous infrared space telescopes. This meant that the faint, low-mass systems expected to populate void environments at these cosmic epochs were finally within observational reach. The second was spectroscopic resolution. Webb's spectrograph could decompose the light from these faint galaxies into sufficiently detailed spectra to measure emission line strengths, absorption features, and continuum shapes needed for determining stellar masses, gas phase metallicities, star formation rates, and stellar population ages. No previous facility could accomplish both tasks simultaneously for galaxies in distant, underdense regions. Hubble excelled at imaging, but lacked infrared spectroscopic capability at the wavelengths needed for intermediate redshift galaxy characterization. Ground-based telescopes with large mirrors possessed raw collecting power, but suffered from atmospheric absorption and thermal emission that crippled infrared sensitivity. The Spitzer Space Telescope observed in the infrared from space but had a mirror only 85 centimeters across, insufficient for resolving the internal structures of faint, distant galaxies. Webb closed every one of these gaps at once. The observations relevant to this story emerged from several Webb survey programs targeting fields with extensive pre-existing multi-wavelength coverage. These legacy fields have been observed over previous decades by numerous ground-based and space-based facilities, building deep catalogues of galaxy positions, photometric properties, and spectroscopic redshifts. The accumulated data allowed researchers to map the 3-dimensional distribution of galaxies within these volumes with considerable precision, identifying which regions were overdense, which were average, and which qualified as genuine underdensities. Within one such field, a well-characterized underdense region at intermediate redshift had been identified through prior spectroscopic surveys. The region exhibited galaxy number counts approximately 30 to 40% below the cosmic average at that epoch, qualifying it as a significant underdensity, though not among the most extreme voids known. Its depth and redshift placed it squarely in the regime where Lambda CDM predictions for void galaxy populations were quantitatively specific but observationally untested before Webb. Webb's near-infrared camera captured deep imaging of this region across multiple infrared bands, providing photometric measurements that sampled the spectral energy distributions of galaxies from rest-frame ultraviolet through rest-frame near-infrared wavelengths. The spectral energy distribution of a galaxy encodes information about its stellar mass, dust content, star formation rate, and the age distribution of its stellar populations. By fitting theoretical models to the observed photometry, researchers could extract estimates of these physical properties for each detected galaxy. The near-infrared spectrograph followed up the most scientifically interesting targets with detailed spectroscopic observations. These spectra captured emission lines from ionized gas within the galaxies, including critical diagnostic lines of oxygen, nitrogen, hydrogen, and sulfur. The relative strengths of these emission lines allow direct measurement of gas phase chemical abundances through well-established calibration methods developed over decades of laboratory atomic physics and observational astronomy. The combined photometric and spectroscopic dataset gave researchers an unprecedented view of the galaxy population within and around this intermediate redshift underdensity. For the first time, individual void galaxies at this cosmic epoch could be characterized with the same level of detail previously reserved for nearby galaxies or the brightest systems in dense distant environments. The analysis proceeded through standard methods refined over years of extragalactic survey science. Spectral energy distribution fitting employed Bayesian statistical frameworks that explored large grids of galaxy models varying in stellar mass, star formation history, dust attenuation, and metallicity. Emission line measurements used automated fitting routines that modeled line profiles, subtracted underlying continuum emission, and computed line flux ratios with carefully propagated uncertainties. Morphological analysis employed parametric fitting codes that decomposed galaxy surface brightness profiles into disk and bulge components, measuring structural parameters including effective radius, Cercic index, and axis ratio. Each step followed established protocols. Each measurement carried quantified uncertainties. The methodology was conservative and designed to minimize the risk of systematic biases inflating the derived galaxy properties. Researchers were not looking for surprises. They were conducting a survey and expected the results to confirm what simulations predicted. The stellar mass measurements arrived first, and they were immediately puzzling. Spectral energy distribution fitting returned stellar mass estimates for void galaxies that consistently exceeded the predictions from Lambda CDM simulations, matched to the same underdensity depth and redshift. The discrepancy was not confined to a few outlying objects. It appeared across the population. The median stellar mass of the void galaxy sample sat approximately a factor of 2 to 3 above the median, predicted by simulations for galaxies in environments of comparable density at that epoch. In absolute terms, several void galaxies returned stellar mass estimates in the range of 10 to 20 billion solar masses. The simulation expectation for the most massive galaxies in a void of this depth at this redshift peaked at roughly 5 to 8 billion solar masses, with the majority of the population falling well below that range. The observed galaxies were not impossibly massive. Galaxies of 10 to 20 billion solar masses are entirely normal in filament and moderate density environments, but they were unexpectedly massive for their specific environmental context. They were heavier than void galaxies at that epoch had any theoretical reason to be. Researchers immediately scrutinized the mass estimates for systematic biases. Stellar mass derivations from spectral energy distribution fitting are sensitive to assumptions about the stellar initial mass function, the shape of the star formation history prior, the dust attenuation law, and the metallicity of the stellar populations. Each of these assumptions introduces uncertainty, and combinations of assumptions can shift mass estimates upward or downward by factors that could potentially account for the observed discrepancy. The team tested multiple combinations. They varied the initial mass function between standard choices. They relaxed the star formation history priors to allow both rising and declining histories. They tested different dust attenuation curves appropriate for different galaxy types. Under every reasonable combination of assumptions, the void galaxy masses remained elevated relative to predictions. The specific numerical values shifted modestly depending on the modeling choices, but the qualitative result proved robust. These galaxies were more massive than their environment predicted, regardless of how the fitting was configured. Stellar mass alone, however, would not have generated significant concern. mass estimates are model-dependent, and a factor of 2 discrepancy between observations and simulations falls within the range that optimistic researchers might attribute to modelling uncertainties on both the observational and theoretical sides. The finding was noted with interest, but could have been filed as a curiosity awaiting further investigation. Then, the metallicity measurements arrived. Webb's near-infrared spectrograph captured emission lines from ionized hydrogen-2 regions within several of the void galaxies, the hot gas clouds surrounding young massive stars, where ultraviolet radiation excites atoms into higher energy states that subsequently decay by emitting photons at characteristic wavelengths. The ratios between specific emission lines serve as thermometers and chemical abundance indicators, revealing the temperature, density, and elemental composition of the ionized gas. The oxygen abundance is the standard proxy for overall gas phase metallicity in extragalactic astronomy. Oxygen is the most abundant metal in the universe, produced primarily in massive stars and distributed through core collapse supernovae. Its emission lines are among the strongest and most readily detected in galaxy spectra. The ratio of certain oxygen lines to hydrogen lines has been calibrated against direct temperature-based abundance measurements in thousands of nearby galaxies, providing a robust conversion between observable line ratios and physical oxygen abundance. When researchers applied these standard calibrations to the Webb spectra of void galaxies, the resulting oxygen abundances were significantly higher than Lambda CDM predictions for their environment. Multiple void galaxies in the sample returned oxygen abundances approaching or exceeding the solar value. The simulation prediction for galaxies at this stellar mass, in this environmental density at this redshift, centered on oxygen abundances roughly 40 to 60% of solar, with few objects expected above 70%. The discrepancy in metallicity was harder to dismiss than the mass discrepancy. Emission line metallicity measurements depend on atomic physics rather than stellar population modeling. The calibrations have been refined over decades using independent methods. While systematic uncertainties exist, particularly in the choice of calibration method, they are generally not large enough to shift measurements from 60% solar to 100% solar. The observed metallicities were genuinely elevated above predictions by amounts that exceeded plausible measurement uncertainties. Higher metallicity carries direct implications for star formation history because it requires more cumulative stellar processing than the models anticipated. Every heavy atom in a galaxy's interstellar medium was forged inside a star that has already completed its life cycle. The oxygen detected in these void galaxies' emission spectra had been produced by massive stars that formed, burned through their nuclear fuel, and exploded as supernovae, scattering newly synthesized elements into the surrounding gas. Finding elevated metallicities meant that these galaxies had hosted more generations of stellar birth and death than their void environment should have permitted by that cosmic epoch. This finding reinforced the stellar mass discrepancy rather than contradicting it. More stellar mass and higher metallicity pointed in the same direction. These void galaxies had been forming stars more vigorously and for longer than simulations predicted. The two measurements were independently derived from different aspects of the data: photometric fitting for stellar mass and spectroscopic line ratios for metallicity. Yet they converged on the same conclusion: the galaxies were more evolved than they should have been. The morphological analysis added a third dimension to the emerging picture. Webb's angular resolution in the near-infrared, approximately 60 to 70 milliarc seconds depending on wavelength, corresponded to physical scales of roughly 500 parsecs at the redshift of the void galaxies. This resolution was sufficient to distinguish between different structural components within each galaxy, separating central bulges from surrounding disks and measuring the relative contribution of each component to the total light. The expectation from Lambda CDM was unambiguous. Void galaxies at intermediate redshift should be almost exclusively disk-dominated systems. The low interaction rates in void environments should prevent the merger-driven bulge formation that builds classical bulge components in denser settings. Any bulge-like central concentration should be minimal, likely a pseudo-bulge produced by slow internal secular evolution rather than a classical bulge built through violent relaxation during a merger event. Several galaxies in the observed sample did show disk-dominated structures consistent with this prediction. Their surface brightness profiles were well described by exponential disk models with low Cerseic indices and negligible central excesses. These objects matched expectations and raised no concerns. But a subset of the void galaxies displayed something different. Their surface brightness profiles required a two-component fit, an exponential disk plus a concentrated central component with a Cerseic index elevated above the pure disk value. The central concentrations were not as prominent as classical bulges in massive elliptical galaxies, but they were more developed than the pseudo-bulges expected from secular evolution alone in isolated environments. Their structural parameters fell in an intermediate regime, more concentrated than pure secular pseudo-bulges, but less concentrated than the classical bulges built by major mergers. This intermediate morphology suggested that these galaxies had experienced dynamical processes beyond what pure isolation should provide. Either they had undergone minor mergers, gravitational encounters with smaller companion galaxies that deposited mass and kinetic energy into the central regions, or internal instabilities had operated more aggressively than models predicted. Both scenarios implied more activity and more structural processing than the void environment was expected to generate. The fraction of void galaxies displaying these intermediate morphologies was modest. Not every object showed a detectable bulge component, but the fraction exceeded the simulation prediction, which expected essentially zero classical or intermediate bulge components in void galaxies at this epoch. Finding even a handful of such objects in a small sample suggested that the underlying rate of dynamical processing in voids was higher than modelled. The fourth and arguably most revealing aspect of the analysis involved the star formation histories reconstructed through full spectral fitting. By modelling the complete spectral energy distribution of each galaxy, including both the broadband photometry and the spectroscopic data, researchers could constrain when the bulk of each galaxy's stellar mass was assembled. The technique works by comparing the observed spectrum against a library of synthetic spectra generated from stellar population models, spanning a wide range of formation times, durations, metallicity histories, and dust properties. Bayesian fitting algorithms explore this high-dimensional parameter space, identifying the combinations of star formation history parameters that best reproduce the observations while marginalizing over uncertainties in other parameters. The reconstructed histories revealed that several void galaxies had experienced their primary epoch of star formation earlier than simulations predicted. Rather than building stellar mass gradually over an extended period, through the slow, steady conversion of accreted gas, as the standard void formation picture prescribed, some of these galaxies showed evidence of substantial star formation activity concentrated in a burst or extended episode that occurred within the first few billion years of cosmic history. These early formation episodes produced stellar populations with ages and spectral characteristics more typical of galaxies in moderately dense environments than galaxies in deep voids. The mass-weighted ages, which reflect when the bulk of stellar mass formed, were older than predicted. The spectral signatures of evolved stellar populations, including strong 4,000 angstrom breaks and weak hydrogen Balmer absorption lines, indicating a deficit of young hot stars relative to older cooler populations, were more prominent than void models anticipated. The implication was that star formation in these void galaxies had not proceeded at the leisurely pace that their environment should have imposed. Something had enabled or triggered more efficient early stellar mass assembly than the models could reproduce. The galaxies had gotten a developmental head start that current simulations did not account for. Considered collectively, the four lines of evidence created a coherent but troubling picture. Higher stellar masses, elevated metallicities, unexpectedly developed morphological structures, and earlier star formation episodes all pointed in the same direction. These void galaxies were systematically more evolved than Lambda CDM predicted for their environmental context and cosmic epoch, No single measurement might have been convincing on its own. Each carried uncertainties and could be individually challenged through various systematic arguments. But the convergence of 4 independent diagnostics on the same conclusion was difficult to dismiss as coincidence or artifact. The research teams who analysed these data began the painstaking process of comparison with state-of-the-art cosmological simulations. The illustrious TNG simulation suite provided the primary point of comparison. This project represents one of the most ambitious efforts in computational astrophysics, modelling the formation and evolution of galaxies within cosmological volumes using magnetohydrodynamic simulations that track dark matter, gas, stars, and supermassive black holes simultaneously. The simulations incorporate detailed prescriptions for gas cooling, star formation, stellar feedback through supernovae and stellar winds, and active galactic nuclei feedback through energy injection from accreting black holes. They have been validated against a wide range of observed galaxy properties, including stellar mass functions, size-mass relations, color distributions, and gas fractions across multiple cosmic epochs. Researchers identified void regions within the illustrious TNG volumes that match the observed underdensity in depth and redshift. They extracted the simulated galaxy populations within these regions and compared their properties directly against the Webb observations using identical analysis methods applied to both datasets. The comparison was unambiguous. Simulated void galaxies were systematically less massive, less chemically enriched, and morphologically simpler than the observed sample. The median stellar mass in the simulations fell below the observed median by roughly a factor of 2. Simulated metallicities tracked the lower end of the observed distribution rather than its center. Bulge components were almost entirely absent from simulated void galaxies at this epoch, in contrast to the intermediate bulge fractions observed in the Webb data. Star formation histories peaked later in the simulations than the observations indicated. The Eagle simulation, developed by a separate collaboration using different numerical methods and independently calibrated subgrid physics, produced qualitatively similar results. Void galaxies in Eagle were less evolved than the Webb observations at the same environmental density and cosmic epoch. The SIMBA simulation framework, employing yet another independent approach to modelling galaxy formation, showed comparable discrepancies. The consistency across multiple simulation suites was informative. It indicated that the disagreement between observation and theory did not stem from idiosyncratic choices in any single simulation code. Whatever was causing the discrepancy lay deeper, in assumptions or physical processes shared across all current modelling approaches. The problem was not that one particular simulation failed. The problem was that the best available tools in the field, despite their independent construction and calibration, all underestimated the evolutionary state of galaxies in void environments at intermediate redshift. The scientific community responded with careful attention but measured caution. The first concern raised was sample selection. Correctly identifying which galaxies genuinely reside inside a void requires precise knowledge of the three-dimensional matter distribution surrounding them. If the void boundaries were slightly mischaracterized, galaxies located in filamentary substructure at the void periphery might be incorrectly classified as void members. These edge galaxies, living in mildly overdense environments rather than the void interior, would naturally show more evolved properties, potentially biasing the sample toward higher masses and metallicities without implying any failure in void formation physics. Webb's spectroscopic data provided partial protection against this concern. By delivering precise redshifts for galaxies in the targeted region, the observations allowed researchers to refine the three-dimensional density map and apply stricter criteria for void membership. Restricting the analysis to only the most isolated galaxies, those with the clearest underdense surroundings in all 3 spatial dimensions, reduced the sample size but did not eliminate the discrepancy. Even the most conservative membership cuts left a population of genuine void galaxies whose properties exceeded model predictions. The second concern involved cosmic variance. The universe is a single realization of a stochastic process. Any particular void might, by chance, contain an unusually rich or unusually poor galaxy population simply because the initial quantum fluctuations that seeded its formation happened to produce a locally atypical outcome. Observing one void and finding it deviant does not prove the models are wrong. It might simply mean this specific void drew an unusual hand from the cosmic deck. Addressing cosmic variance rigorously requires observing many voids at similar redshifts and determining whether the discrepancy persists across the population or is confined to isolated cases. Webb's field of view and the observational expense of deep spectroscopy limit the number of void regions that can be characterized in detail within any single observing cycle. The current dataset covers only a small number of void regions at the relevant redshift. Statistical conclusions must therefore remain provisional until a larger sample accumulates. However, the researchers noted a feature of the data that weakened the cosmic variance explanation. The discrepancy was not driven by a few extreme outliers that might represent rare statistical fluctuations. Instead, the entire distribution of void galaxy properties appeared shifted toward more evolved values. The median and the interquartile range both exceeded predictions, not just the tail. This population-level shift is harder to produce through random variance than a scenario involving a handful of anomalous objects within an otherwise normal distribution. A third line of scrutiny targeted potential systematic biases in the observational analysis. Could the spectral energy distribution fitting be overestimating stellar masses due to incorrect assumptions about dust, star formation history shape, or stellar initial mass function? Could the metallicity calibrations be returning artificially elevated oxygen abundances for galaxies at this specific redshift, perhaps due to nitrogen contamination of the line ratios or evolution in the calibration relations themselves? Each of these possibilities was investigated. Dust assumptions were varied across a wide range. Star formation history priors were relaxed to include both parametric and non-parametric forms. Alternative metallicity calibrations were applied. The results proved qualitatively robust under all tested variations. Specific numerical values shifted at the margins, but the central conclusion survived every systematic test the teams could devise. The void galaxies were more evolved than simulations predicted, regardless of which reasonable methodological choices were applied. The finding connected naturally to a broader pattern emerging from Webb observations across multiple science programs during its first 2 years of operation. In several independent contexts, Webb was revealing that galaxy formation in the early and intermediate age universe had been more efficient than Lambda CDM simulations reproduced. Massive galaxies were appearing at higher redshifts than expected. Quenched galaxies, systems that had already ceased forming stars, were being identified at cosmic epochs when simulations predicted they should still be actively building stellar mass. Chemical enrichment appeared to proceed more rapidly than feedback-regulated models allowed. The void galaxy observations slotted into this emerging narrative as another expression of the same underlying tension. If galaxy formation was systematically more efficient than current models captured, the effect should manifest across all environments, not just the dense regions where the earliest and most massive galaxies form. Voids, as the lowest density extreme, would show the discrepancy differently, not through impossibly massive galaxies that belong in cluster cores, but through modestly oversized and over-enriched galaxies that exceeded the conservative predictions appropriate for their sparse surroundings. This interpretation had the advantage of parsimony. Rather than requiring a separate void-specific explanation, the discrepancy could reflect a single underlying issue with how simulations handle star formation efficiency or feedback strength, an issue that propagates across all environments, but manifests most clearly in the regimes where predictions are most sensitive to these parameters. But parsimony is not proof. Connecting the void findings to the broader early galaxy tension was intellectually satisfying but did not identify the specific physical mechanism responsible. Multiple very different modifications to the underlying physics could produce similar shifts in galaxy properties. Increased star formation efficiency, decreased feedback effectiveness, enhanced gas accretion rates, modified cooling functions, altered dark matter halo assembly histories. Each of these adjustments would push galaxy populations toward more evolved states at earlier times. Distinguishing between them required more than the observation that void galaxies were too evolved. It required understanding precisely how and why they were too evolved. The observation raised another unsettling implication that several research groups noted independently. If void galaxies at intermediate redshift were more evolved than simulations predicted, then the calibration data used to tune those simulations might itself carry unrecognized biases. Subgrid models for star formation and feedback are calibrated against observed galaxy populations at specific redshifts, typically the present epoch or the recent cosmic past. If the calibration data is drawn primarily from average and overdense environments, the resulting subgrid prescriptions might accurately reproduce galaxy formation in those settings, while failing in the low-density extreme. The void discrepancy might then reflect not missing fundamental physics, but incomplete calibration of empirical models. This interpretation was both more encouraging and more concerning than the alternatives. More encouraging because it suggested the fix might be relatively straightforward, extending calibration samples to include void environments and adjusting subgrid parameters accordingly. More concerning because it implied that current simulations might have hidden environmental dependencies in their predictions, errors that would only become apparent when tested against data from environments significantly different from the training set. Conference presentations of the early results generated animated discussion within the extragalactic astronomy community. The findings were published in peer-reviewed journals and posted on preprint servers, where they attracted substantial attention. Several independent groups began planning follow-up observations to test whether the discrepancy reproduced in additional void regions at similar and different redshifts. Simulation teams began running targeted experiments, modifying specific subgrid parameters and testing whether any single adjustment could bring void galaxy predictions into agreement with observations without degrading the fit to galaxy populations in other environments. What emerged from the initial wave of analysis was not a crisis. It was a clearly defined scientific problem with testable hypotheses and a realistic path toward resolution. The observations did not suggest that voids were impossible, that Lambda CDM was fundamentally broken, or that the cosmic web had been misunderstood. They suggested something more specific and ultimately more productive. The physics governing how galaxies form and evolve inside the lowest density environments in the cosmos was not yet fully captured by the theoretical tools at hand. The void was not misbehaving. Our models of what voids should produce were incomplete. That incompleteness now had an empirical shape. It could be measured, quantified, compared against theoretical alternatives, and progressively narrowed through additional observations. The James Webb Space Telescope had done what the most powerful scientific instruments always do. It had not answered a question. It had revealed that the question was deeper than anyone realized, and it had given scientists the data they needed to begin constructing a better answer. The galaxies drifting through one of the emptiest regions in the observable universe had refused to match the script that 3 decades of theoretical development had written for them. Something about their formation had proceeded faster, earlier, or more efficiently than any current simulation reproduced. Identifying what that something was would require rethinking assumptions about processes occurring in environments where, until recently, scientists believed almost nothing interesting could happen. The void had spoken. And the scientific community was only beginning to decode what it said. Science does not advance through certainty. It advances through the disciplined management of uncertainty. Every observation that refuses to match a prediction represents not a failure, but an opportunity. A place where nature is offering information that the existing framework cannot yet accommodate. The history of physics is littered with discrepancies that initially appeared minor and ultimately reshaped entire fields. The anomalous precession of Mercury's orbit was a tiny deviation from Newtonian gravity that eventually demanded general relativity. The ultraviolet catastrophe in black-body radiation was a modest disagreement between classical theory and laboratory measurements that required quantum mechanics. Not every discrepancy leads to revolution. Most are resolved through improved measurements, corrected calculations, or refined models. But every discrepancy deserves serious investigation because scientists cannot know in advance which category it belongs to. The discrepancy between Webb's void galaxy observations and Lambda CDM predictions falls squarely into this investigative phase. It is too significant to ignore and too preliminary to interpret definitively. Multiple possible explanations exist, each carrying different implications for how well we understand the universe. The coming years of observation, simulation, and theoretical development will determine which explanation survives contact with accumulated evidence. The first category of explanations focuses on dark matter halo assembly in underdense environments. In the standard framework, galaxies form inside gravitationally bound concentrations of dark matter. The properties of these halos, their masses, formation times, concentration profiles, and merger histories determine the raw material available for galaxy formation. The halo mass function, which describes how many halos of each mass exist in a given volume, is one of the most fundamental predictions of Lambda CDM. It has been computed analytically and confirmed through numerical simulations to high precision in average density environments. But the halo mass function inside voids carries larger uncertainties than its counterpart in denser regions. Simulations that model cosmological volumes large enough to contain many voids necessarily sacrifice resolution within individual void interiors. The computational cost of tracking dark matter particles scales with the number of particles simulated. Achieving high resolution throughout a volume large enough to contain statistically meaningful void samples requires particle counts that push even modern supercomputers to their limits. Most production-scale simulations compromise by adopting resolution levels that adequately resolve halos in average and overdense regions, while potentially under-resolving the smallest halos in underdense environments. This resolution limitation could systematically bias the predicted void galaxy population. If some halos in void interiors fall below the resolution threshold and are missed entirely, the simulated halo mass function would appear shifted downward relative to the true distribution. Galaxies that should form inside these unresolved halos would be absent from the simulation output. The predicted void galaxy population would then appear less massive and less numerous than reality, producing exactly the kind of discrepancy Webb observed. Several research groups have begun testing this hypothesis by running dedicated high-resolution simulations of individual void regions. These zoom simulations sacrifice cosmological volume in favor of enhanced resolution within a single void. Tracking dark matter particle interactions at mass scales 10 to 100 times finer than typical production simulations achieve. Early results from pilot studies suggest that increased resolution does produce somewhat more massive halos within void interiors, but the magnitude of the effect varies between studies and does not yet clearly account for the full observational discrepancy. A related possibility involves the tidal environment inside voids and its effect on halo formation timing. The gravitational tidal field describes how the pull of gravity varies across space, creating compressive forces along some axes and stretching forces along others. In filaments and cluster environments, tidal fields are strong and complex, shaped by multiple nearby massive structures. Inside voids, the tidal field is weaker and more uniform, dominated by the large-scale underdensity rather than local mass concentrations. Some theoretical work suggests that the quieter tidal environment inside voids could allow halos to begin collapsing slightly earlier than in more disturbed settings. Without strong external tidal forces disrupting the initial stages of gravitational collapse, the first dark matter concentrations in void regions might cross the threshold for halo formation marginally sooner than equivalent overdensities in tidally active environments. An earlier start, even by a few 100 million years, would give void galaxies more time to form stars and accumulate metals before the cosmic epoch at which Webb observed them. This tidal timing effect falls under the broader umbrella of assembly bias, the dependence of galaxy properties on factors beyond simple halo mass. Assembly bias has been debated extensively in the galaxy formation literature. Its strength and even its existence remain contested for different galaxy populations and environments. If assembly bias operates in void environments in ways not captured by current analytic prescriptions or insufficiently resolved simulations, it could contribute meaningfully to the observed discrepancy. Testing the assembly bias hypothesis requires simulations specifically designed to isolate tidal effects on halo formation in void environments. These simulations must track halo assembly histories with sufficient temporal resolution to detect formation time differences of a few 100 million years, a demanding requirement that limits the number of objects that can be studied in detail. Nevertheless, several groups are pursuing this approach, and results expected within the next few years should clarify whether tidal timing contributes to the void galaxy discrepancy. The second category of explanations targets the gas physics and star formation prescriptions used in hydrodynamic simulations. Converting gas into stars is the most uncertain step in the entire galaxy formation pipeline. The physical processes governing star formation span an enormous range of scales, from the kilopascant scale accretion of gas onto galaxies down to the subparsec collapse of individual molecular cloud cores into protostars. No simulation resolves this full range. Instead, simulations employ subgrid models that encapsulate the net effect of unresolved small-scale physics into effective prescriptions operating at the resolution scale. These subgrid prescriptions are empirically calibrated. Researchers adjust free parameters until the simulation output matches a selected set of observational benchmarks, typically the galaxy stellar mass function, the galaxy size-mass relation, and the cosmic star formation rate density at specific redshifts. The calibration data is drawn overwhelmingly from galaxies in average and overdense environments, because those are the environments where the most complete observational samples exist. If the physics of star formation depends on environmental factors not captured in the calibration process, the resulting subgrid prescriptions could systematically mispredict galaxy properties in extreme environments. Void interiors represent the lowest density regime in the cosmos, far from the environmental conditions that dominate calibration datasets. Subtle dependencies of star formation efficiency on gas density, metallicity, or ambient radiation field that are unimportant in average environments could become significant in the rarefied conditions inside voids. One specific possibility involves the cooling of gas in low metallicity environments. Heavy elements play a critical role in enabling interstellar gas to radiate away thermal energy and collapse into star-forming clouds. Metal-rich gas cools efficiently through emission from ionized carbon, oxygen, silicon, and iron atoms. Metal-poor gas loses this efficient cooling channel and must rely on less effective processes, primarily molecular hydrogen cooling at low temperatures and hydrogen Lyman alpha emission at higher temperatures. Standard subgrid models typically assume that gas cooling follows a metallicity-dependent function, calibrated from theoretical atomic physics calculations and observational constraints in nearby galaxies. But the transition between metal-dominated cooling and molecular hydrogen-dominated cooling occurs in a metallicity regime that is poorly sampled observationally. If molecular hydrogen formation proceeds more efficiently in void conditions than current models assume, perhaps because the lower ambient radiation field in voids destroys fewer molecular hydrogen molecules through photodissociation, gas cooling could be faster than predicted. Faster cooling leads to more rapid condensation into star-forming clouds, higher star formation rates, and ultimately more stellar mass and higher metallicity at any given epoch. Supernova feedback represents another area of significant subgrid uncertainty relevant to void environments. When massive stars explode as supernovae, they inject kinetic energy and thermal energy into the surrounding interstellar medium. This feedback heats gas, drives outflows from galaxies, and regulates the overall efficiency of star formation. In massive galaxies with deep gravitational potential wells, supernova-driven outflows are contained, and the expelled gas eventually recycles back into the galaxy. In low-mass galaxies with shallow potential wells, the same feedback can permanently eject gas from the galaxy, shutting down star formation. Void galaxies predominantly reside in low-mass halos with shallow gravitational wells. Standard subgrid models therefore predict that supernova feedback should be highly effective at suppressing star formation in void galaxies, keeping their stellar masses low and their gas reservoirs largely unprocessed. But the effectiveness of feedback depends on how the energy couples to the surrounding gas, which in turn depends on the density, temperature, and geometry of the interstellar medium at scales well below simulation resolution. If feedback in void galaxies is less effective at ejecting gas than subgrid models assume, perhaps because the lower gas densities in void environments reduce the radiative losses that sap energy from supernova-driven shocks, then more gas would remain available for star formation. The net star formation efficiency would be higher than predicted, producing more massive and more chemically enriched galaxies. Some simulation groups have begun experimenting with environment-dependent feedback prescriptions that reduce ejection efficiency in low-density regions. Preliminary results show improved agreement with the Webb observations, but the modifications are not yet uniquely constrained by the data. The third category of explanations involves the filamentary substructure that exists even within cosmic voids. Voids are not perfectly uniform underdensities. They contain faint internal structures, tenuous threads of dark matter and gas that connect the sparse galaxy populations within the void to the surrounding cosmic web. These internal filaments are far less dense than the major filaments separating voids. They contain too little mass to host rich galaxy populations or to be easily detected by current galaxy surveys, but they are predicted to exist by Lambda CDM simulations when run at sufficiently high resolution, and they could play a significant role in feeding void galaxies with gas from larger distances than their immediate surroundings. If gas flows along these faint internal filaments more efficiently than current models capture, void galaxies could receive sustained fuel supplies that enable higher star formation rates than their local environment would otherwise permit. The galaxy would effectively reach beyond its immediate neighborhood, drawing on gas reservoirs distributed along filamentary channels that extend tens of millions of light-years into the surrounding void interior. This filamentary feeding mechanism is well established for galaxies in average density environments. Cold mode accretion along cosmic web filaments is recognized as a primary fuel source for galaxy growth at intermediate and high redshifts. The question is whether equivalent accretion occurs along the much fainter filaments inside voids, and whether current simulations resolve these structures with sufficient fidelity to capture the associated gas flows. Evidence from the highest resolution void simulations suggests that internal filamentary structure is richer and more dynamically significant than coarser simulations indicate. When resolution improves, faint filaments appear that were absent at lower resolution, and gas accretion rates onto void galaxies increase accordingly. This resolution dependence implies that standard production simulations may systematically underpredict the gas supply available to void galaxies, leading to underestimates of their stellar mass growth and chemical enrichment. Detecting these faint filaments observationally is extraordinarily challenging, but not entirely impossible. The gas within them should produce faint Lyman alpha emission, as hydrogen atoms are excited by the metagalactic ultraviolet background radiation. Dedicated surveys using integral field spectrographs on large ground-based telescopes have detected Lyman alpha emission from cosmic web filaments in overdense environments. Extending these detections to the much fainter filaments inside voids would require significantly deeper exposures, but falls within the theoretical capabilities of next-generation facilities. Webb itself may contribute to this effort indirectly. By mapping the spatial distribution of galaxies within void regions with greater completeness than previous surveys, Webb can identify galaxy alignments that trace underlying filamentary substructure, even when the filaments themselves remain undetected. If void galaxies preferentially align along linear or curvilinear structures rather than distributing randomly, this alignment would constitute indirect evidence for internal filaments channeling both matter and galaxy formation within the void. Beyond these three main categories, several more speculative possibilities deserve mention. Some researchers have considered whether modifications to the dark matter model could alter structure formation in void environments. Standard Lambda CDM assumes cold dark matter particles that interact only through gravity. Alternative models propose warm dark matter, self-interacting dark matter, or fuzzy dark matter, each of which modifies halo formation in specific ways. Warm dark matter suppresses the formation of the smallest halos while leaving larger halos relatively unaffected. Self-interacting dark matter produces halos with modified internal density profiles. Fuzzy dark matter introduces quantum pressure effects that alter halo formation on small scales. Each alternative dark matter model produces different predictions for void galaxy populations. Some would exacerbate the discrepancy with observations, while others might ameliorate it. Comprehensive comparisons between void galaxy observations and alternative dark matter predictions are underway but require substantial computational investment because each model demands its own suite of large volume simulations. Another speculative avenue involves early dark energy models, theoretical frameworks in which dark energy played a more significant role at early cosmic times than the standard cosmological constant allows. If dark energy was stronger during the first few billion years of cosmic history, void expansion would have been faster during that period, potentially altering the dynamics of halo formation and gas accretion within void interiors in ways that differ from the standard timeline. Early dark energy models have been proposed to address other cosmological tensions, including the Hubble tension between local and cosmic microwave background measurements of the expansion rate. If these models prove necessary for other reasons, their consequences for void galaxy formation would need to be computed and compared against the Webb observations. The observational program needed to resolve the discrepancy is already taking shape. Webb itself will contribute additional void galaxy characterizations in upcoming observing cycles. Several approved programs target void regions at multiple redshifts, extending the baseline of cosmic epochs at which void galaxy properties can be measured. If the discrepancy persists across a range of redshifts, it would strengthen the case for a systematic modeling issue. If it appears only at specific epochs, it would constrain the relevant timescale and potentially point toward a specific physical mechanism that operates differently at different times. The Euclid Space Telescope is conducting a wide-area survey, covering approximately 15,000 square degrees of sky with both photometric imaging and slitless spectroscopy. This survey will identify thousands of cosmic voids across a broad redshift range and measure the statistical properties of their galaxy populations. While Euclid's spectroscopic resolution is lower than Webb's, its enormous sky coverage provides the statistical power needed to test whether the void galaxy discrepancy is a universal phenomenon or confined to specific void regions. The Vera C. Rubin Observatory, which achieved first light in mid-2025 and is expected to begin its legacy survey of space and time in early 2026, will complement Euclid with ground-based photometric coverage of unprecedented depth across the southern sky. Rubin's ability to detect extremely faint galaxies, including the low-surface brightness systems expected to dominate void populations, will extend the void galaxy census to luminosity regimes inaccessible to current surveys. The Dark Energy Spectroscopic Instrument continues its 5-year survey program, accumulating spectroscopic redshifts for tens of millions of galaxies and quasars. This dataset will provide the most precise 3-dimensional map of the cosmic web ever constructed, allowing void identification and boundary characterization with accuracy far exceeding previous surveys. Combined with targeted Webb follow-up of galaxies within well-defined voids, the DESI data will establish whether the properties of void galaxy populations match Lambda CDM predictions at the statistical level that only large samples can provide. On the simulation front, several major projects are underway that will improve theoretical predictions for void galaxy populations. The Flamingo Simulation Suite, one of the largest cosmological hydrodynamic simulations ever completed, includes sufficient volume to capture many void regions while maintaining resolution adequate for characterizing their galaxy populations. Comparisons between flamingo void galaxies and observational samples are in progress and will provide updated theoretical benchmarks against which Webb data can be evaluated. The Millennium TNG project combines an extremely large cosmological volume with state-of-the-art galaxy formation physics, enabling statistical studies of rare environments, including the deepest voids in the computational volume. This simulation will test whether the void galaxy discrepancy persists when galaxy formation models are updated with the latest calibration data and numerical techniques. Individual research groups are pursuing targeted zoom simulations of specific void regions, investing computational resources in resolving the internal structure and galaxy populations of single voids at resolution levels 10 to 100 times finer than production cosmological simulations achieve. These focused efforts sacrifice statistical sample size in favor of physical detail, testing whether the discrepancy disappears when simulations resolve the faint filamentary substructure and small-scale halo populations that production simulations miss. What remains genuinely unknown is substantial. We do not yet know whether the discrepancy between Webb observations and Lambda CDM predictions reflects a fundamental shortcoming in the standard cosmological model or a correctable deficiency in the simulation tools used to generate predictions from that model. These are very different diagnoses with very different implications. If the model itself is incomplete, meaning the basic physical framework governing structure formation needs modification, the consequences would extend far beyond void studies into fundamental physics. If the simulations are incomplete, meaning the model is correct but the computational implementation fails to capture relevant processes at adequate resolution, the fix is technical rather than revolutionary. We do not yet know whether the discrepancy persists across a wide range of void depths, redshifts, and cosmic environments, or whether it is confined to specific conditions. A universal discrepancy appearing wherever void galaxies are observed in sufficient detail would constitute a much stronger challenge to the theoretical framework than a discrepancy appearing only in certain void regions at certain epochs. The current observational sample is too small to distinguish between these scenarios. We do not yet know which specific physical process is primarily responsible for producing void galaxies that are more evolved than predicted. The candidate explanations described in this section are not mutually exclusive. Enhanced halo assembly, modified gas cooling, reduced feedback efficiency, and filamentary accretion could all contribute simultaneously, with their relative importance varying between different void regions and different cosmic epochs. Disentangling these contributions will require observations that probe each process independently, rather than measuring only the aggregate galaxy properties that reflect all processes combined. We do not yet know whether the void galaxy discrepancy is related to the broader pattern of unexpectedly mature galaxies that Webb has discovered at high redshifts. The connection seems plausible on physical grounds, but establishing it rigorously requires demonstrating that the same modification to galaxy formation physics simultaneously resolves the void discrepancy and the high redshift galaxy abundance tension. No single proposed modification has yet been shown to accomplish this, and we do not yet know what voids will teach us about dark energy when their galaxy populations are better understood. The entire scientific case for using voids as dark energy laboratories rests on accurately modelling the gravitational and gas dynamical processes occurring within them. If our models of void galaxy formation are incomplete, the systematic uncertainties in void-based dark energy measurements may be larger than currently estimated. Resolving the galaxy formation discrepancy is therefore a prerequisite for realizing the full potential of voids as cosmological probes. These unknowns do not represent failure. They represent the active frontier of scientific investigation, the boundary between what has been established and what remains to be discovered. Every unknown carries within it the possibility of a breakthrough. Every unanswered question defines a research program that could reshape how we understand the cosmos. The James Webb Space Telescope looked into a cosmic void and found galaxies that were more mature than our best models predicted. This finding does not overthrow the standard model of cosmology. Lambda CDM remains the most successful framework ever developed for describing the large-scale evolution of the universe. No single discrepancy in void galaxy properties, however significant, invalidates a framework that has survived 3 decades of increasingly precise observational tests across multiple independent lines of investigation. But it does mean the framework is incomplete in ways that matter. Something about how galaxies form in the lowest density environments in the cosmos is not yet captured in our equations, our simulations, or our theoretical understanding. The emptiness was not as empty as we assumed. The void was not as barren as we predicted. The galaxies drifting through one of the most desolate regions in the observable universe had built themselves up more than any model said they could. There is something quietly profound in this. Humanity has a long history of assuming that emptiness is simple, that where nothing appears to exist, nothing interesting can occur, that the blank spaces on the map are blank because they contain nothing worth mapping, and repeatedly, across every scale of investigation, this assumption has proven wrong. The vacuum of quantum field theory seethes with virtual particles. The apparent void of interstellar space contains the molecular clouds from which stars are born. The seemingly empty expanses between galaxy clusters harbour the faint filaments of the cosmic web. Now the interiors of cosmic voids themselves have yielded their own version of this lesson. The places defined by absence turned out to contain presence. The regions characterized by what they lack turned out to possess more than expected. The empty map was not empty. It was simply awaiting an instrument powerful enough to read what was written there. This is perhaps the deepest message the void has to offer. Not a specific correction to a specific equation, though that correction will eventually come. Not a particular modification to a particular simulation parameter, though those modifications are already being tested. But something more fundamental about the relationship between human expectation and cosmic reality. We build models of the universe based on what we have observed. Those models are extraordinary achievements, representing centuries of accumulated insight refined through rigorous confrontation with evidence. But they are always provisional. They are always incomplete. And they are always most vulnerable in the places we have not yet looked. The void was one of those places. Webb looked. And the universe, as it always does, turned out to be richer than the model we had built to describe it. The story is not over. It is, in the most meaningful sense, just beginning. The next generation of telescopes will observe more voids in greater detail across a wider range of cosmic epochs. The next generation of simulations will resolve physical processes at finer scales with greater fidelity. The next generation of theoretical frameworks will incorporate whatever new physics these observations demand. Each step will bring us closer to understanding why the emptiest places in the cosmos produce galaxies more evolved than we predicted. And if history is any guide, each step will also reveal new questions we had not thought to ask. That is the nature of the enterprise. Science does not converge on a final answer. It converges on better questions. The void has given us a better question. Answering it will require patience, precision, and the willingness to be surprised again. Somewhere in the observable universe, right now, photons are leaving void galaxies that no telescope has yet observed. Those photons carry information about how matter assembles itself in the emptiest environments nature provides. They are crossing millions of light years of nearly empty space, drifting through the darkness between the cosmic web's luminous threads. Some of them will arrive at Earth years or decades from now, landing on the detectors of telescopes that have not yet been designed. When they arrive, they will tell us something we do not currently know. They will refine or revise or possibly overturn the conclusions we have drawn from the data already in hand. They will extend the map into territory we cannot yet see. The void is not empty. It never was. And the map is not finished. It never will be.